Hey guys, my name is Simon Fiedler and welcome to another exciting Houdini tutorial, and this time we want to talk about volume trails. I want to explain to you what volume trails are and why they're useful, and we'll try to build a nice little setup here. I have this example where there's a tree-like structure and we will recreate them, and the cool thing about this tool is that we start off with curves like this. So we basically simply paint those curves into the viewport, and our volume trail setup will create those nice curly trails, and we will have great control with the sliders here over the noise value, how curled they are or not curled at all, and we have this great structure, and everything as usual is fully procedural. So let's dive in and start with a new scene, and then I'll try to explain to you what this stuff is all about. Alright, an empty scene. So before we start, I want to explain to you what volume trails are and how they work. So let's take a look at this. As you have seen, it was my example file were basically curves which followed my initial curves that I drew by myself, and volume trails are basically, if you're coming from Cinema 4D, you might know the tracer, where you can trace particles and other objects and they start to draw lines into our 3D world. And volume trails are something similar. The only difference is that you don't have to press play and run a simulation and really draw the curves. They are just there, and the curve follows a vector volume. So first of all, let's try to find out what this is. If you are using Houdini for a while, or if you know stuff like Turbulence FD and Cinema 4D or other voxel-based tools, you might know what a volume is. So a volume is basically a grid. Let me paint this here. This is a very rough grid, something like that. I painted now in 2D, but of course in reality it's a three-dimensional grid, but that's the same. And if you have something like a smoke simulation or something like that, that's most of the times also a voxel grid, and it's a scalar volume, which means that each voxel holds a density value, for example, for smoke. So this voxel here has the density of 1, this one here is 0.5, this has 0, 0, 1, 0.7, 0.2, whatever. So each voxel can store information about the density of the smoke in this voxel. So each voxel has one value that is stored. So the cool thing is that we also have vector volumes in Houdini, which means each voxel can store more than one value at a time. And in our case, each voxel will store a vector, so a direction. So it will look like this. We have in this voxel this direction, this one here, this here, and so on. So we can store as much directions as we want in our grid, and maybe in the end it looks something like this, like that. And this is then our vector volume, which is a 3D, it's like a 3D map which gives you directions. And for our volume trails we specify a point in space, let's say here for example, or let's say here. Here's our point in space. And the volume trail node will now look up in this vector volume in which direction this voxel points, and then it starts to draw a line until we come to the first to the next voxel, and then it will follow this direction. So now it goes there, and then it will go there, and then it will go there, and there, and there, and this one will push us out. So the volume trail basically uses points as a start point and then draws a line following the directions of a vector volume. Need to drink something, sorry. And with that we can first of all visualize volumes and vector volumes especially. For example, a curl noise or stuff, very nice, and create very cool abstract structures. But I will also explain how we can create such a vector volume in a very specific way that we exactly know where these arrows point, and define the the end shape of our volume trails by ourselves. So let's start here. So first of all, I want to show you how volume trails in general work. I'll disable the grid here, that we have an empty viewport. And we'll start off with a geo node, which is just a placeholder. Call this one volume trails. And dive into this node by double clicking it and delete the file node. Then we are now in an empty container. And we start off with a circle. So create a circle, which gives us this disk. And we set the orientation to ZX, that it's flat on the floor, and make it smaller, maybe 0.2. Yeah, that looks good. And now we create a point using a scatter node. So click here, set the display flag on the scatter, and then you see points. And it's 1000 points, and we simply set that to 1. And we have 1 point here. I will make that bigger just for the screen recording, that you can see it better. If you also want to make points bigger, go with your mouse over your viewport and press D, like display, and then under geometry you'll find point size, and you can simply increase that. And it's a little bit more obvious for you guys that you can see it. So now we have our, let's call it a seed point where everything starts. And next thing is we need a volume, a vector volume. So for that, let's simply create a volume. So hit tab, type volume, set the display flag on that, and then you see this nice little bounding box. And just for visualization, we will make it bigger. So on the size, let's make it 5 by 5 by 5. So it's a nice volume here. And for now the volume is empty, so this is why you only see a bounding box here and nothing more. So let's change that. First of all, our rank of the volume. In here it says scalar. And as I said, scalar just stores one value at a time per voxel, and we set that to vector. And then our volume needs a name, and we will call this volume velocity. Like that. And you could set, if you want, an initial value. So if I type in 1 here, you see that we instantly see a previous of that. You can also do that in all other dimensions, but it doesn't make much sense because we write in our own values in the next node. So simply leave that to 0. And now it's time to bring in some data here, because now our volume is just empty. So if I would connect the scatter and the volume to our volume trails, then there's nothing to trace. So no trails in there. So, and to write in something our volume, we will use a volume VOP. So this is the same type of node that you can use like a point VOP or an attribute VOP. So VOP is a vex operator, which means you can manipulate the data from of this object inside of the network here. If you're coming from Cinema 4D, the stuff inside here is pretty familiar to express, so it looks almost the same. A lot of nodes are the same. Some of them work a little bit different, but the basic concept is the same, I would say. So let's connect the volume to our volume VOP, set the display flag on that one, and dive into it by double clicking it. Let me just get a little bit more space here. And you can see that we have our inputs on the left and outputs on the right. And there's only one thing connected, which is density. In our case, we don't care about density because we're using a vector volume. So simply delete the volume output, and then we will write our own outputs here. So let's create a curl noise, for example. Which looks like this. You can also use all kinds of other noises. The only important thing is that you set your noise to a 3D noise, that you get directions and not only float values. And then simply connect the position to the position input of the noise. This position here that comes out here is not a point in space or something. This is the position of each voxel. So now each voxel will look up its own position in the noise and check which direction is generated by the noise, and then stores it back into the voxel, if that makes sense. Okay, now we have an output here, noise, and now we have to write it into an attribute that we can read out later. And for that, we use a bind export node. So if you want to bring in data in here, which is not in that list, let's say you have stored any specific attribute on your voxel, and it's not in this list, you use a bind node to bring it in, and a bind export to write it out again. So this is something like a save node, which stores it to your attributes. And we call this one velocity, and set the type to vector. And now you can connect your noise to the output. And that's basically it. And now you can see a first result here. Something like a cloudy thing, whatever. And now we go back one level. Just click on this one or hit the U button on your keyboard. Now you're back. And we have our volume here and we have our point here. And now it's time to bring those two together with our volume trails. And we have two inputs. If you go with your middle mouse button on those inputs, you can see the instructions. Those are the points to trail, and on the right one is the velocity volumes. So just connect everything together and set the display flag here. And we can see there's a little line. Ah, fantastic. Yeah, and that's it for today's tutorial. No, just kidding. We continue and make it longer. So you can just simply use this slider here, make it longer. Let's set it to something like 30 maybe. And then you get this line. And you see that the resolution is not very high on that one, so we don't have a lot of points. And those points are actually our voxel borders. So if you increase the resolution of your volume, those lines will also get more high res. So simply click on the volume. And uniform sampling is right now set to 10, so simply increase that to 20 or 40, 60 maybe, and then you will end up with something like that. The reason why the shape changes so much if you change the resolution is that your noise, if the voxels are too big, it's possible that specific values of the noise are skipped, simply because it's not accurate enough. And then your line goes in a totally different direction, so just that you know that. But this is already a pretty interesting shape, I think. And the cool part starts if you don't have one point as a seed point, but a lot of them. So if you, let's keep the display flag on the volume trail and click on scatter, and then simply increase the number of points here to maybe something like 500. Oh, by the way, you can switch a viewport to full screen if you hit Control B. You also get back with that. And you can do that in every window to full screen stuff. So this is actually a visualization of a curl noise. So our points start in the middle and then they follow the noise. Of course, this is now a little bit chaotic, so it will look better if we simply adjust our noise. So let's go into the volume bob. And we want to have the controls for that outside of this node. So we middle click on frequency, for example, promote parameter, and then you get this little knot. And if we go back one level and select the volume bob node, you can see that the frequency settings are now here. So let's decrease this value. If you go on frequency, hit the middle mouse button, you get the value ladder, and then you can go to the step size and then simply drag to the left. And then you can see you get this nice interactive way of changing values. Now you have a pretty interesting shape already. Yeah, I like stuff like that. It's a cool thing. The thing right now is it's just a noise and not very predictable what happens in there. And it gets more interesting, of course, if you can simply decide how this volume should look like and what those lines follow. So let's do this. So let's dive into here and let's see. Let's get rid of those two nodes, the volume and the volume bob. And how many points do we have right now? Now we have 500 points. Let's decrease that again to, let's say, on the scatter node, let's type in 20 maybe. 20 looks good to me. And as I said earlier, we want to try to use curves to define the exact shape of the volume. And I would like to draw those curves outside of the setup so that we just reference them in here. So let's go back one level, create another geonode and call this one curves. So we're now on scene level, make sure here is scene up there. Create a geonode, call it curves, dive in there. It's not working. No, it's working. Okay. Delete the file node in there, and then we can simply create a curve node. Right. By default, the viewport will be empty, and then you can use this tool here, the manipulator, and if you click it, you can start to draw your curve here. There's one nice thing in Houdini. You can see that right now we are moving on the ground plane. So if I click here in the middle, we can create our first point in the perspective view. If I now move around, I'm always on the ground plane. And let's say I go here, and if you then hold down Shift, you can change the height level of your curve. And if you release Shift again, you will stay on this plane. And you can see this very nice visualization in the viewport. So let's click here, second point, and just try to draw an interesting shape. Maybe something like that, and like that. Okay, this is my curve. And we will also set the curve type, if you click on the node, from polygon to NURBS, that we have a round curve, just because it looks better in this case. So this is our first step. So let's go back, disable the curves here maybe, and enable volume trails again, and jump in here. So now we need to bring in our curves from the other network into this one, and to do so we use an object merge node. So this is basically something like a shortcut to the other setup, and in there you can specify the object. So let's click on that one and simply grab the curves object here in your tree. So not the one which is in there. This is only the one specific object. We use the object itself, because later we will draw several curve objects in there, and they are all collected in this one. So take this one and hit accept. And if we now set the display flag on that one, you will see that we brought in the curve from the other graph to this one. Okay, now we somehow have to generate some directions, so we want to know where this curve is pointing. And we could do this using the tangent of the curve itself. So, but before we can do that, we need to generate them. So as you've seen, we've created a NURBS curve, which means we don't have a lot of points here. These are actually the points that we have. So in order to get a lot of points on that one, we will simply resample the curve. So use a resample node, connect that one, and then you have the length slider here where you can define how fine it's subdivided. So let's take something like this maybe. I hope you can see the points. And now we want to calculate the tangent of each point. So basically the tangent is always a vector which points exactly in the direction of the curve on each point. We will visualize that in a second so you can see it exactly. And to calculate that, there's a nice node called polyframe. Connect that. set the display flag on this one. And in here, we set the entity from primitives to points, that we store the tangent on the point. We don't need the normal, so you can disable that. And tangent name, it's called tangent u. We simply call it tangent. So just remove the u from here. And if we now click middle mouse button on our polyframe and hold it, you can see that we now have two point attributes. One is the position of the point, and the other one is the tangent, the one that we just created. So now it's time to visualize that in our viewport, that we can see what just happened. And a great way in Houdini to visualize stuff are visualizers. To activate them, also just go with your mouse over the viewport and hit D, like display. And then there's a tab called visualizers. And in here we can visualize a lot of stuff. So basically all kind of attributes or data which is stored on a point you can visualize in the viewport. And here under scene visualizers, click the plus, click on marker, then you get this window. So we call this one tangent, label is also tangent, and attribute that we want to read out, you can click on this arrow. Oh, we can see one here. So don't click on this arrow, just write in here tangent. And as soon as you do that, you can see some numbers in here. And this is always x, y, z of our of the vector, because the style is set to text. So right now you see really the text visualization in the viewport, but you can set the style from text to vector, and then you get this one. And you can also set show arrow tips, then you can see the direction better. And you can adjust the scale of the vectors, just that they're not too big or not too small, just that you can see them. Something like that maybe. And close the window. And if you want to deactivate visualizers in your viewport or activate them again, simply hit this button here. So if you want to get rid of them, click that, click it again, and you can see them. So now you can see we generated a lot of vectors, and they always point into the direction where the curve is going. They're just the wrong way around. There is now several options to invert those tangents. You can simply go outside of here into the curves, and I think on the curves node itself there's a checkbox for reverse. If you hit that, they are the other way around. But we won't do that. We go back, and we go back in here, and we use an attribute wrangle node and write something in there. And not because it's better or smarter or something like that. We just do it because I know how it works, because I started to learn Vex. And I'm very proud that I can write something like that, so I use it. So you don't have to use it, because it's actually a little bit stupid. But if you're interested how this works, do it like I do. Let's take an attribute wrangle. And this is really, really easy. Connect it to the first port, set the display flag here, and then we can write vector at tangent. So this, we tell the wrangle node now to read out the vector attribute called tangent, and that equals, if you wrote that it's a vector once, you don't have to write it again. So simply add tangent times -1, semicolon. And now watch the viewport. Bling! They're reversed. Fantastic. You can see I'm a high-level programmer now. So let's continue. Our tangents are reversed now. So now they are pointing from our starting point, from our root, in the right direction. So now we need to take those vectors and write it into a volume. We don't have a volume, so we should generate one. And I would like to have a volume which is always a little bit bigger than our curve, so that we don't have to adjust that by hand. So if I change the shape of my curve, I want the volume to adapt this. You can simply create a volume, an empty volume, and connect that, and then the volume will snap to the bounding box of our object. But the thing is, I would like to have it a little bit bigger than our bounding box. So to do that, there's one node called bounds, or bound. And if you connect that, you get a box, which is actually our bounding box. So not very fancy for the moment. But in there's a padding value. And you can set some values in there, let's say 0.5, 0.5 on the lower and upper padding in all directions, and you can see that the bounding box simply gets a little bit bigger than the initial one. And now we connect our volume to that. Well, this is out of the recording area. Volume still out of the recording area. So simply take a volume. That's wrong. Volume analysis. Volume. Alright, connect that, make it visible, and here we are. We have our volume, which is a little bit bigger than the bounding box of our curve. Alright, so now basically we do the same steps than we did before. We click on our volume, set the rank from scalar to vector, call it velocity, and maybe increase the let's do it like this. The uniform sampling divisions is now set to 10, and I think it always takes the longest axis of our bounding box and divides it by 10, which determines the size of your voxels. Let's set it from max axis to by size. That's a little bit better, I think. And simply leave it to 0.1. And then we can adjust the size of our volumes very easy later on. Okay, and now it's time to bring in the our tangents that we created. Where was it? Here. Those tangents, and write those tangents as a value in our volume. And for that, we again need a volume VOP. Okay, the volume VOP, and connect that. And maybe we should name this stuff here a little bit. So the polyframe we can call create tangent. Attribute wrangle is reverse tangent. And here create val volume. Alright, set the display flag on the volume VOP. And double click on that. Oh no, let's go back, I forgot something. Up here where we have our reverse tangents, we use this state here and simply connect this node to the second input of our volume VOP. So we want to bring in the data that we created here also in our volume VOP and read that out and write that back into our volume. So let's double click and let's see what we can do here. I need more space. We delete the density again. And then we create a bind export. Set it to the end of our chain and simply call this velocity again. And set the type to vector. Great. Okay, now we need to read out those tangents that we created, and as you remember, we connected the tangents to the second input of our volume VOP. And you can see the input here. So we can basically get the data from here, and we will import the points of our curve as a point cloud. This is a very smart way to import data, and it's very fast. So to read that in, there is a node called PC open, which is point cloud open. Looks like this. And the node wants to know a file, so basically which object should be brought in as a point cloud, and we connect input 2 to the file. And then it has a position input, so basically we need the position of our voxel. So each voxel looks up what value a point from this point cloud has in this position. And then here we get a handle where all the data that our points have come out, and we have to decide what we want to read out. And for that we use a PC filter, point cloud filter. So imagine every point has 10 attributes or something, and they are coming out of here all at once, and you have to decide which attribute you want to read out. So connect the handle to handle on the filter, and on this node here you can decide which one you want to have. And in our case we want the tangent. This is a vector channel, that's correct. And now we simply take this value and write it into our velocity. And as soon as we do that, you can see there's looks like a very wispy smoke trail in here. So we already write some information from our curve into our volume. If you click on the PC Open node, you will find a search radius. So basically all the points on our curve have a search radius, and if we increase that, you can see that it becomes thicker. So we can do that, simply set it to 1. So then that every point has an area of influence, and this can be pretty big. And then let's go back, simply hit U on your keyboard, and now we have basically our very simple velocity volume. So let's take the circle, the scatter and the volume trail on the right side again. Now let's set it to the left side, it's better that we don't cross the lines. So the volume trail in the middle, and then you can simply connect our generated volume to the volume trail and set the flag on that one. And you can see that our points, which are down here, are now traced, and they follow exactly the shape of our curve. So that's basically part 1. And a pretty cool way to generate something like that, very procedural, and you don't have to simulate any particles to trace them, you get the result instantly. This is very nice. Okay, now let's continue. Let's say we want to add a little bit of noise in there. Or even better, let's say our source is very big, something like that, so that some of our points are outside of the influence radius. So let's make it another way. Sorry, I'm not so well prepared as usual. Let's use a noise. We build in the noise first, that we have some turbulence in our traced lines. So let's make the circle smaller again, maybe 0.3. That looks good. So if we want some turbulence in our trails, we simply have to turbulence our noise. So this is a very cool thing. So let's go back into our volume bob, and at this point, right before we plug the result of our tangent in the velocity, we have to bring in a noise in here and mix it in. So let's create a curl noise again, for example. Sample the position. And then maybe just add it on top of our tangent. So let's use the tangent, add our noise, and the result should be there. Then it looks like this. And I'm pretty sure that this is a little bit too much, but let's expose a few parameters first. So click on frequency, promote parameter, maybe offset, promote parameter, and amplitude, promote parameter. So now you have these 3 knobs again, and if you go back 1 level, we can access them here. So let's take a look at our volume trails. Click on that. And you can see that our trails now roughly follow the shape of our curve, but some of them just get lost somewhere. You should see it better if we increase the number of scattered points, something like that. But it's already a pretty interesting result, so you can play around with the amplitude, something like that, but you can see that some of them simply get lost. They are influenced too much by the noise. So it would be cool if the noise is more intense in the when it's close to the original curve, so to this one. So the intensity when they are close to the curve should be very high, and then on the outside it should be very low. And additionally, if there's a curve, a trail getting lost somewhere, it would be cool if the volume could push it back. So we will create another volume or another vector inside of our volume bob, which always points to the closest point on the curve. So if there's a point here, for example, when it's outside of a specific value, a distance, we want a volume to push it back in this direction. So let me maybe make a very nice drawing here. Let's save. Okay, let's say we have our curve here. So right now our trails follow this one, but they have some noise here, right? So it goes something like this. And if a curve goes in that direction, when we reached a certain distance, something like that, this distance, we want our volume to push it back in this direction. And then the curve goes back here. So basically our volume that we create looks something like this. We have the curve here. And then in here we have a lot of noise. But further out we have something like this. So all the vectors which surround it push the stuff towards the center of our spine, let's call it a spine, and in there we have a lot of noise. We'll see if that makes sense if we now build it. It's for me right now it's a little bit hard to explain, but we will see. So we have our tangent and we have our noise in here, and now we want to create something that looks like this. So a lot of vectors that always point, no matter where you are, choose a random position, this one, and then there's a vector which points directly to the curve. Alright, so let's jump into our volume again. Oh, let's go back and set the flag on the volume trail that we can see the result. Go back to the volume bob, and we will create another vector field. So this is very basic vector math. So the cool thing is we get a position out of our volume bob. So each voxel can sample its position. So let's say it's this position. And then we have our curve brought in as a point cloud. So let's say on the point cloud, here's a point. So each point has this search radius, which gives the closest point, right? So we set the search radius to 1, something like this, so pretty big. So this point here knows that this point is the closest. And to get the vector between those two, you simply subtract the position of this point from the position of this point, or the voxel in this case, this is a voxel. And then you get the vector which is in between them. And the rule is tip first, so if you want a vector that points from here to here, and let's say this is point A and this is point B, if you want a vector which points from here to here, you subtract A minus B. If you want a vector that points from here to here, you subtract B, Jesus Christ, B minus A. Okay, that's the dry theory. Let's try this. Here we have a point cloud. So we need the position of the points of our curve, right? And with this PC filter, we decided that we want to read out the tangent of the points. But of course, we can also read out the position of the points. To do that, we simply copy our PC filter node. And instead of the tangent, we read out the position. So just type in capital P, then you get the position of the point on the curve. And here we have the position of our voxel. So we create a subtract. And we first plug in the position of the point cloud. And in the second port, we use the position of the voxel. And just that we can see that, connect the result to our velocity for a second, and then it looks something like this. So obviously this doesn't help very much, and what I like to do is just for visualization, you can see that something's happening here. So they get basically sucked in and snapped to the first point that they can find. But just to visualize our field better, we won't use these points here. I like to use another one, so let's delete this connection here, disconnect. And then simply we create a scatter node and connect that to our resampled curve, so to the second node. Click on that, and then basically we create a lot of points on top of our curve, and we reduce the number to, let's say, 500, 300, 300 looks good. And after that, use a jitter, point jitter, that just pushes the points in random directions, like that. So you can just jitter them and distribute them a little bit, and maybe crank up the scale a little bit, something like that, so that you get a nice amount of points surrounding our curve. And now we use those points and connect that to the volume trail. And this is only a temporary thing, so we just use it right now to set up our volume correctly. So then you have a pretty good chance to understand what's happening here. Excuse me. So you see that each point starts here and then goes directly to the first point on the curve. So this now our volume looks like this. And if we go back to our volume bob, dive in there, and then don't connect this result here, but connect our earlier result maybe, where we mixed the tangent with our noise. You can see it looks like this. So you just have a pretty good visualization of your volume in space. And now we want to mix this one here with the one here, so that we get the best of both worlds. So we want to use this field here as long as the trails are close enough to our original drawn curve, and when they are too far away, we want to use this one here, that they get pushed back. And let me think about that. Maybe it would be cool to mix that one here with our tangent, that they don't go straight here, but straight and also in the direction of our of our curve. So let's do it like this. We disconnect our tangent. Let me plug that one in shortly. So let's forget about this noise here for a second. So just disconnect that one here. We will build that in later again. So we have our tangent and we have our this field here, which points always to the closest point on the curve. And now we want to mix them together. And to do that, we have a node called mix. So this is very easy. So in the first one, we connect our tangent, and in the second one, we connect the stuff that we see right now. And then we connect the result. And now you see that, which also looks pretty cool. This is a 50-50 mix of both vector fields. So basically you always get a force that drags the points to the center of your curve and also in the direction of the tangent. And on your mix you have a bias slider. So right now it's set to 0.5, which means 50% of the one and 50% of the other vector field. And you can simply slide that across however you want. This is pretty useful. And I would like to have this automatic that when points are very far away, we only want to use that force, and when they are very close to the curve, we only want to use that force. So we need to get a value that drives this bias value down here. And easiest way would be to measure the distance of our point to the curve, right? So we have our position here, and we have the point on the curve here, and we subtracted them, which means we already have the vector which points from the voxel position to the closest point on the curve. Now we only need to know how long this vector is. And for that we have a node called length. So simply connect that. So here we get the length. And our bias is always between 0 and 1, but maybe we don't want to use that exactly as our length parameter. So maybe we want a fall off between 0 and 0.5 or something. And for that we use a fit range, which is basically the range mapper in Expresso in Cinema 4D. Connect that one to value. and the shift output to the bias. Then it looks like this. Already a pretty cool result. And now you have this source min and source max, and you can adjust those now to define exactly what the shape should look like. So for example, you can say, okay, don't start at 0, start at 0.2, and then the maximum reach should be 1.5 and all this stuff. So you can define the shape here pretty good. So maybe we should expose those parameters, those two, to the outside world. So right click on source min, promote parameter, and source max, promote parameter. And if we hit U, we have here our little field where we can specify the shape and the look of our field pretty good. Alright, so it's time to mix our noise back in. So jump into that, and let's see, here's our noise. And we simply, let's try this, we simply add the noise to the mixed result here. I'm not sure if it works, but let's see. Okay, that's a little bit much. I think we have to decrease the amplitude of our noise. That looks much better, something like that, maybe. Yeah, why not? So let's take our circle and the scattered points from the beginning again and plug them into our volume trail. Take a look at the result. And this doesn't look too bad, so maybe decrease the number of points, something like that. Yeah, nice, interesting shape. And now you can adjust everything as you want, so more noise, you can make it wider, something like that. And simply shape to whatever you want it to be. Make the noise give it more frequency. Yeah, that's cool. Alright, so let me connect back our visualization points for the noise that we can see it. Maybe it would also be a good idea to get rid of noise here on the outside where it simply gets pushed back. So let's jump back into our volume warp and let's see. So we have our curl noise here. And we have our fit here. So let's see if we can somehow mix those two together. The amplitude, no. We will create a second fit and connect the length of our that we created here, that we calculated here. Plug it back in and connect that to amplitude. So let's get rid of this one. To get rid of this, not just double click it, then you can see the node here and just delete it. And then we connect the shift to amplitude. And now our curve is gone. This is weird. Let's go back. Okay, here it is. So dive back in there. And now we have to adjust that fit here. So if the point is super close to our curve, we want a lot of noise. So let's set this to 1. And if it's far away, we want no noise at all. And here we can define how far away it can be. It's great. And this is our output strength. So we can decide how strong the noise should be in there. And this is how far it reaches out. So let's also expose this. So this is source max, promote. And let me double click that so that we can give it another name that it's just more obvious. So this is noise fall off. So let's set it as a name and as a label. And the other one was destination min. Middle mouse button, promote, and double click on this node. And call it noise amplitude. Something like that. Alright. And now we should have them here. Correct. So noise fall off. Here you can decide how far the noise reaches out. and the second slider says how strong the noise is, right? So something like that maybe. And if you now connect your the initial point here again, you have pretty good control of what's happening here, and it's also super fast, which is amazing. Alright, so I'll connect that one back. Sorry, I jump between those two all the time, so because I can see what's happening in there so good. And the last thing which I would like to introduce is a rotation, so that we have like a vortex, that our vectors around the curve don't only follow it and have some noise, but also rotate in itself like a vortex. So for that we have to open our perfect visualization tool here again and think about how this works. So there's a thing in vector mathematics called a cross product. So let me use just that. So let's say we have this point here, and we have the closest point of the curve, and we already calculated that one, right? So the vector that points from here to there, and we know the tangent of this curve, so we know that one. And if you now cross this vector with this vector, you get a third vector. And the third vector points, that's hard to draw right now, the third vector points directly at us. So let's try a new sketch. So this is our point. So this is the one. Then we have the tangent. Let's draw it on this side. This is the tangent. And if I cross those two vectors, I get a third vector, which is 90-degree angle to those two vectors, right? So this is like an x, y, z axis. So we can, we can create a new field here and then mix them back together. So because this vector actually, no matter where you are around this, no matter where you are around our curve, the cross product always points in this direction. So this is basically our rotational force that we want to bring in now. So let's do this. So we remember we have to cross the vector from our voxel to the closest point on the curve with the tangent, right? Okay, so let's dive into the velocity volume. And you need a lot of space for this kind of stuff, but it's worth it. So let's see, we need the position, the closest position. What do we need? We need this one here. So this node basically is that one here, or that one, where we subtracted the two positions from each other. This is here. So we create a cross product node and connect that one. And we have to cross it with the tangent, which comes out here, if I remember correct, right? So use that one and connect it here, make some space. So this should be our new field. And as usual for visualization, simply connect this cross product to our velocity. And then you can see this result here. So this looks amazing. It's just all the points that we scattered around our curve now show a perfect circle surrounding our curve, and it will always follow it. So this itself is already cool. And now we mix everything back together. I just see that we almost have 1 hour of tutorial, but it wouldn't make much sense to stop now. So I think I hope you like it. If that was all that you wanted to know about volume trails, you can stop now. If not, stay with me and we will combine all this stuff now. So this here was our initial field, and this here is what we had here. So I would say it would make sense to bring the rotation and the other stuff together before we add the noise on top of it. So basically we mix that result and that result. We mix those two together. So let's create another mix node, connect them, input, input, and we simply have it to 50-50. Connect that here, and you can see that we get very nice vortex shape where our fields surround the initial curve and always point to the center but surround around the curve. And if we click on the mix and just pull the slider to each side, you can blend perfectly. If you set it to 1, you only get rotation forces. If you set it to 0, you only get the other force. So let's connect this mix to the second input of our add that we added back together with our noise, and connect that one to our velocity. Now it would be cool to have the bias of our rotation force. Let's bring that in. Oh, that looks so cool. So it would be great to also access this slider outside of the setup. So we will also middle click, promote parameter, double click on that one to open it up and call it rotation, maybe, in name and label. If we now go back, we should have all the controls that we want on our volume bob. So you can define the rotation here, the strength of it, the noise amplitude, we have the noise frequency up here, something like that, noise fall off, all the stuff that you would like to have. And now we can connect our initial scatter points, which are on the floor here again. And now you basically start off down there. Just the rotation. Oh, this is so cool. Noise amplitude, bring it down maybe, something like that. Yeah, and you're basically done. And on the volume trail you can now easily animate the length and let it grow however you want. So this is of course a very nice example now what this volume trail does, and we have our own custom volume which does exactly what we want. And just to finish this tutorial here, I want to show you something pretty cool. Since everything in here is generated automatically, you can very easy now extend the whole setup because it's a field that you generate, right? So the size of our volume is dependent on the bounding box of our curve, etc. And if you now change the curve, that brings everything in. So if I make this one visible again, so this was our curve, right? If you now simply draw another curve, everything will work exactly the same. So I will just show you that. Let's get rid, so a little bit more space on the viewport that we can see that. So we have our flag on the volume trail, go up one level on scene level, and here we have our curves, right? So double click that. And you can now easily add some curves. Let's say, for example, you copy that one simply and take the manipulator and now change the curve to something like, let's say like this maybe. I will just create a random different shape and now create a merge node to bring those two curves back together. So simply select both and connect them and set the flag on the merge here. Then you can see both, right? So you can also delete some points, so simply click on the point and delete it. Maybe bend this to this side, something like that maybe. And I will create a third curve also connected to the merge. And let's say we want to go in this direction, something like that maybe. Sorry, here we are again. I just brought in the curves that I've drawn earlier for my example because they had a nicer shape, and I spent a little bit more time on drawing these. So the rest of the setup is exactly the same. So let's go back, and you can see that our result looks pretty cool. Sick. Go into the volume trails, and now we can adjust stuff like the noise amplitude, frequency maybe a little bit higher, the fall off of the noise. So if you have it super low, you can see that you get results like these, very curvy, interesting looking lines. Then you have to adjust the volume resolution, of course. So if you change that to a higher volume, then it should get more accurate. 0.2 maybe. That takes a little bit longer. Something like that. So this is a pretty cool looking shape. Let me bring in a little bit more noise amplitude, like this. Voxel size is very small now. I just did 0.4. Simply play around with those values. Let's fall off. I'll just try to get an interesting looking shape here. Yeah, why not? So this is a nice way to use volume trails. I hope you liked it so far. And there's one little bonus that I would like to show, because you created now a vector field, so a velocity volume which stores directions, right? And we use that for our volume trails to simply draw lines. The cool thing is that this velocity volume can be used for other stuff too. So for example, if you now create particles on the floor, you can simply advect those particles with this same field, which will mean that the particles follow exactly that field. And it's so easy that we will do that now also. We have a 1-hour tutorial now, but that shouldn't stop us from doing more cool stuff. So simply take the circle, for example, and create a pop net. The pop network, if you connect the circle to the pop net and set the display flag on this one and simply hit play, you can see that it will just create some particles here on the floor. So it's filling up very, very quickly. I will decrease the size of the points again because it's a little bit too big now. You can't see anything. Alright, so we have particles. I will make the circle a little bit bigger, something like that. And if we hit play, we can see, okay, particles. So simply jump into the pop net. Then you get this basic setup here. This is just a merge, you can delete that. On this object, the setup will store the particles, and on this one it will create the particles. But we don't have to mess around with that, just to show that example. And there's one node called pop advect by volumes. And you simply plug that in here, so between the object where your particles are generated and between your solver. And in there, you have to specify your volume, but there's also a nice way where how you can bring in this volume that you created. Simply set that one to second context geometry, and then you have to write in the field name, which is not called vel in our case, it's called velocity. Let's go back one level, and we set it to second input, which is that one. So take your volume VOP, where you defined all your values for the volume, and connect that to the second port here. And if you go back in here, and by default the pop advect volumes is set to update force. This generates a lot of, it generates forces in each voxel, which means they add. So the particles get faster and faster, so they won't follow the shape exactly. Simply set the advection type from update force to update velocity, for example. And now let's zoom out a little bit and simply hit play. And then you can see that you get nice particles which follow exactly the shape of your volume, and will fill up the shape that you created earlier completely. So is this cool? This is cool. And this will also react if you have like rigid body dynamics down here. So some objects, they will also react to this force, or should be possible with cloth or everything that you can advect. And I think this is super cool and very nice to. Also, if you're only working with particles, it's super cool to visualize the stuff that you're doing. So that's basically it. So I hope you liked this tutorial. Let me know what you think and write it in the comments. I'm more than happy for all the comments that you guys write me. I read that stuff and I try to answer all the questions, and let me know what you would like to see next. And I'll see you next time. Bye bye.